Hello friends, welcome to my channel Explore with Joyeeta.
After the successful Chandrayaan-3 mission, the Indian Space Research Organization ISRO has launched India's first solar mission. On September 2, 2023 at 11:50 IST, the Polar Satellite Launch Vehicle PSLV C-57 accomplished a successful launch of Aditya L1 from the second launch pad of the Satish Dhawan Space Center STSC located in Sriharikota. Aditya L1 is the first space-based Indian mission to study the Sun. Aditya L1 is a satellite dedicated to the comprehensive study of the Sun. It has 7 distinct payloads, all developed indigenously. 5 by ISRO and 2 by Indian academic institutes in collaboration with ISRO. Aditya L1 will be able to provide observations of the Sun's photosphere, chromosphere and corona. Aditya in Sanskrit means the Sun. L1 here refers to Lagrange point. Lagrange points are positions in space where the gravitational forces of a two-body system, like the Sun and Earth, produce enhanced regions of attraction and repulsion. These can be used by spacecraft as parking spots in space to remain in a fixed position with minimum fuel consumption. The Lagrange points are positions where the gravitational pull of two large masses precisely equals the centripetal force required for a small object to move with them. This mathematical problem, known as the general three-body problem, was considered by Italian-French mathematician Joseph Louis Lagrange in his prize-winning paper. There are 5 special points where a small mass can orbit in a constant pattern with 2 larger masses. Of the 5 Lagrange points, 3 are unstable and 2 are stable. The unstable Lagrange points, labeled L1, L2 and L3, lie along the line connecting the 2 large masses. The stable Lagrange points, labeled L4 and L5, form the apex of 2 equilateral triangles that have the large masses at their vertices. The L1 point of the Earth-Sun system affords an uninterrupted view of the Sun. According to ISRO, a satellite placed in the halo orbit around the L1 point has the major advantage of continuously viewing the Sun without an occultation or eclipses. This will provide a greater advantage of observing the solar activities and its effects on space weather in real time. This location also allows the satellite to access solar radiation and magnetic storms before they are influenced by Earth's magnetic field and atmosphere. Additionally, the L1 point's gravitational stability minimizes the need for frequent orbital maintenance efforts, optimizing the satellite's operational efficiency. Aditya L1 stays Earth-bound orbits for 16 days, during which it undergoes 5 maneuvers. Subsequently, Aditya L1 undergoes a trans-Lagrangian 1 insertion maneuver, marking the beginning of its 110-day trajectory to the destination around the L1 Lagrange point. Upon arrival at the L1 point, another maneuver binds Aditya L1 to an orbit around L1. The satellite spends its whole mission life orbiting around L1 in an irregularly shaped orbit in a plane roughly perpendicular to the line joining the Earth and the Sun. Aditya L1 will stay approximately 1.5 million kilometers away from Earth, directed towards the Sun, which is about 1% of the Earth-Sun distance. The Sun is a giant sphere of gas and Aditya L1 would study the outer atmosphere of the Sun. Aditya L1 will neither land on the Sun nor approach the Sun any closer. The atmosphere of the Sun is formed by its outer layers. There are primarily three layers that makes up the atmosphere, which is named as the core, the radiative zone, and the convective zone. These are the internal parts of the Sun. Core. The centermost region of the Sun is known as the core. This is the region where hydrogen turns into helium through the nuclear fusion reaction, with temperatures believed to be reaching more than 15 million degrees Celsius. The core is considered to be the hottest region of the Sun. When we move towards the outerward layers, the density and temperature decreases. Radiative zone. Between the core and the convection zone, there lies the radiative zone. By means of radiative diffusion and thermal conduction, the energy in this layer transports outside, which travels in the form of electromagnetic radiation by photons. Bouncing from particle to particle, photons transfer energy. Convection zone. The outermost layer of the Sun's interior is known as the convection zone. This zone uses convection mode to transfer energy. The temperature at its base is about 2 million degrees Celsius. The temperature in this zone is low enough for the heavier ions like carbon, oxygen, nitrogen, iron, and calcium to hold on to some of their electrons. The atmosphere of the Sun is made up of 6 layers. Photosphere. The photosphere has a thickness of about 500 kilometers, and all the visible light from the Sun comes from this layer, with temperature coming down to approximately 5500 degrees Celsius. It is said to be the coolest part of the Sun because with an increase in height, the temperature drops. Sunspots. The dark spots on the surface of the Sun are known as sunspots. This happens because the region becomes darker and cooler than the surroundings due to intense magnetic fields on the surface. The lifetime of sunspots is generally less. It fluctuates from a few days to a few months. Chromosphere. The chromosphere is visible as a dim red ring and it lies just above the photosphere. Only during the solar eclipses, when the photosphere is hidden, visible light from the chromosphere can be seen. With the increase in height, its temperature increases. Corona. The corona layer is the outermost layer of the Sun's atmosphere and it lies above the chromosphere. During a total solar eclipse, it can be seen as a white glowing corona. Up to 2 million degrees Celsius, the temperature on the corona spreads and the reason for it is still unknown. Coronal mass ejections, solar winds and solar flares are the phenomena related to corona. Solar flares. When magnetic energy is suddenly released, immediately flashy and increased brightness occurs, which is known as solar flares. Magnetic irregularities are the reason for their occurrence. Anywhere between 10 to 20 million degrees Celsius, these are magnetic storms that heat up. Solar winds. The flow of energized charged particles at a very high speed is known as solar winds. At a temperature equal to 1 million degrees Celsius, the speed of solar wind is as high as 900 kilometers per second. It is composed of plasma and generally contains protons, electrons, and alpha particles. The primary objectives of Aditya L1 include studying solar winds, which can disrupt Earth's magnetosphere and manifest as awe-inspiring auroras. Study of solar upper atmospheric dynamics, study of chromospheric and coronal heating, physics of the partially ionized plasma, initiation of the coronal mass ejections and flares, observe the on-site particle and plasma environment providing data for the study of particle dynamics from the Sun, physics of solar corona and its heating mechanism, magnetic field topology and magnetic field measurements in the solar corona. There are 7 instruments installed on Aditya L1 which can be called the 7 payloads. First, visible emission line coronagraph, or VELC in short. It will study the coronal layer and observe the coronal mass ejections. Second, Solar Ultraviolet Imaging Telescope, in short, SOOT. It is tasked with imaging the sun's photosphere and chromosphere in the ultraviolet spectrum. Third, Solar Low Energy X-ray Spectrometer, in short, SOLEX. And fourth, High Energy L1 Orbiting X-ray Spectrometer, in short, HELIOS. Both of them will study the X-rays emitted by the sun, especially the X-rays emitted during the solar flares. Fifth, Aditya Solar Winds Particle Experiment, in short, ASPEX. And sixth, Plasma Analyzer Package for Aditya, in short, PAPA. These two will study the solar wind. The last payload is the magnetometer, MAG, which is used to measure magnetic fields. The magnetic fields that reach this L1 point. 4 out of these 7 payloads will directly study the sun, and the remaining 3 payloads will take measurements around the L1 point.
So friends, this was my video today.